he ever published was this one, October 1970, where he described something called Conway's Game of Life, created by an English mathematician called John Conway. Now, as games go, Conway's Game of Life does not look terribly exciting. It is a game for no players, played on an infinite board, and it has 4 rules, the rules of life. The first rule, each of these cells on our grid can either be living or dead. If a cell has 0 or 1 neighbors, it will die of loneliness. If a cell has 2 or 3 neighbors, it survives to another generation. If a cell has 4 or more neighbors, it's like being in London, it dies of overcrowding. Or it moves to Germany, I don't know, but it's not there anymore. And finally, and this is where it gets a little bit spooky weird, if a dead cell has exactly 3 neighbors, it will come back to life. And that's it. That is, you now understand everything that there is to understand about the rules of Conway's Game of Life. Now, when Martin Gardner's article was first published, 1970, very, very few people had computers. And so they used pens and graph paper to play the game of life. And they drew diagrams like this. Now, these 5 shapes are what we call the tetrominoes. They're the 5 Tetris tiles. And this shows you the evolution of each of those shapes under the rules of Conway's Game of Life. But, you know, looking at this, it's like going to a museum where they have the butterflies pinned in a glass case. You can see what the butterfly looks like, but you don't understand anything about a butterfly from looking at this kind of representation. It wasn't until we started using computers to actually simulate this stuff that we really understood the behavior we were looking at. Because these 4 patterns, they all stabilize quickly, but this one over here, this is just going to keep going over and over and over. And once we could visualize things like this, exploring the game of life became addictive. People started saying, you know, are there patterns that will move across the grid and just keep going? Are there limits? Is the game bounded or is it infinite? This was one of the first shapes. This is known as a glider. Repeats itself every 6 generations, and it just keeps crawling across the grid forever. And once we realized gliders were possible, people started looking for more, and they found hundreds of these shapes, spaceships they call them. These incredibly elaborate, beautiful creations that just glide across this grid, driven by 4 simple rules. And that's it. One of the earliest questions that came up in the game of life, can you create patterns that will grow infinitely? It's a guy called Bill Gosper. He was a founding artificial intelligence researcher and computer scientist, some of you may have heard of. And his team at MIT in the 1970s, they created something absolutely wonderful. They created a thing called Gosper's glider gun. Now, what the glider gun is it's a stable configuration, and every 27 generations, it creates a glider and sends these gliders streaming out across the grid. And Gosper's team discovered another, lots of configurations while they were exploring this. They also discovered this thing here, which was called the ITER. Now, we have a glider generator and we have a glider consumer. We can generate signals and we can destroy signals. We have 1 and we have 0. And if we have 1 and 0, we have binary logic, and we can use that to create logic gates. So this thing here is an AND gate built in the game of life. These little highlighted cells are our inputs. Now, what we're going to do, first of all, we're going to start the circuit running, and then we're going to say, OK, we're going to take that blocker out so that our input A becomes true. There we go. A is now switched on. We have no output signal. We only have 1 input. Let's flip the inputs. What happens if we switch B on? Well, B is on, but we still have no output signal, because this is an AND gate. In order to get an output signal in here, we need to enable A and B. We switch on both of those inputs. We switch on our circuit, and there we go. We have an AND gate. Now, the brilliant thing about this is that if you have logic gates, you can make circuits. And if you can make circuits, you can create computers. And if you can create computers, you can run programs, including this program that you may have heard about a little while ago. It's a thing called John Conway's Game of Life. And it goes a little something like this. Now, Conway's game of life is just one of a whole category of systems that exhibit very, very complex behavior based on what look like very, very simple rules, simple inputs. You've